Hi everyone, this is Hal Tasaki. In this online seminar, I'd like to briefly discuss the main results of my recent paper with this title. And actually, there are two videos for this single paper, and now you are watching the shorter version. And that is perfectly okay if you are an expert, but if you're a beginner, if you're not an expert, please think about watching the longer one. Anyway, let's get started. So this is just an ordinary introduction. Our understanding about non-interacting topological insulators is almost complete. We know this periodic table, and there are many rigorous index theories. But interacting topological insulators are not well understood, and we still do not have complete classification. Okay, there are many, many works, probably I'm missing a lot. And there are some mathematically rigorous works, but they are still limited. In this paper, I presented a new rigorous index theory for a class of one-dimensional topological insulator, including the SSH model. And I established the existence of a symmetry-protected topological phase transition in the infinite system, and also the existence of gapless H mode. But I claim that the proof of the theorem is very elementary and simple and short. I don't use any functional analysis, operator algebraic technique, or anything. Okay. You will see. Okay, so let me briefly talk about the SSH model. So I assume that you're familiar with the SSH model. So this is the Hamiltonian. And here, this is on just the nearest neighbor hopping Hamiltonian with this parameter. But the important thing is that we interpret that 2j and 2j plus 1. These sites form a unit cell. Okay. And as you know, in this extreme case, s equals 0, you have this kind of state where the bond is confined in each unit cell. But for s equal 1, you have this state where a bond connects neighboring unit cells. And people call this trivial and this non-trivial. Okay. And so this is a phase diagram. Two phases with unique gap ground states are separated by a critical point. And this is, of course, not characterized by a symmetry breaking or anything, but it's characterized by a topological index. And in this case, the index is called the Zach phase, which is the Berry phase. And it's defined in this way in standard notation. Okay, and it takes 0 throughout this trivial phase and 1 in this non-trivial phase. Okay, but this is a standard expression of Zach phase, but it is also well known that this Zach phase is related to the expectation value of the twist operator or the flux insertion operator of Bloch or Lipschutz lattice in this way. Okay. And these are all standard, but if you're not familiar with this, this is, I think, very interesting and worth understanding. And then if you're not familiar with this, please please watch my longer version of this video, in which I explain this thing in rather detail. Okay, so I think, but anyway, so this relation that relates this topological index nu, which is 0, 1, with this expectation value of the twist operator is essential for us. Okay, now I talk about my result. So this is a class of models that I consider. So this is general Hamiltonian with interaction and possible disorder. T is the hopping amplitude. I assume that it's real and symmetric. And it's 0 when j minus k is even. So this means that you can have hopping between 0 and 1, 0 and 3, but not no hopping between 0 and 2. Okay, and it's short-ranged and it's summable. And for interaction, as for interaction, I assume that it's short-ranged and bounded. Okay. Here's an important corollary of our theorem. Note that the SSH model belongs to this class. Then I prove that H0 SSH and H1 SSH belong to different phases within this space of models. So more precisely, if HS, as usual, is any path of Hamiltonians that connects this and this, and then I prove that HS must go through a phase transition point, where you have either non-unique ground state, gapless ground state, or some discontinuity. This is something I proved rigorously and in an elementary manner. Okay, so the strategy of the proof: the model has no translation invariance, so no band structure. The model has interaction, so you don't have any easy Slater determinant ground state. And we shall study phase transition rigorously. That means we have to work in infinite system. This looks like a very difficult task, but our strategy is to define a Z2 valued index by using the sign of the expectation value of the local twist operator. So this, I use only the expectation value, and this makes the theory very elementary. And actually, the strategy was developed by myself like 3 years ago for quantum spin chains. Remark about the symmetry. This is the symmetry of the model. So first of all, of course, particle number is conserved, so we have U1 symmetry. And I also claim that this Hamiltonian is invariant under the particle Hall transformation, followed by the Gates transformation on one of the sublattices. This is described by this map gamma, which mathematicians call a linear star automorphism. This is the condition. But anyway, C is mapped to C Dagger times this phase factor. And with this transformation, n changes to 1 minus n. And you can easily show with this assumption that this hopping part is invariant. And also from this, you easily find that this interaction part is also invariant. So H is invariant. And by omega, I denote the ground state of the infinite chain. And if you're interested in the rigorous definition, please look at my paper or the longer version of this lecture. But anyway, you can safely assume that this omega A is just this limit. Okay, phi ground state L is a ground state of a finite chain with suitable boundary condition. So this is a finite body expectation value, and you take just infinite volume limit. A is any local operator. Okay, and if the ground state is unique, then it's also gamma invariant in this sense. Okay, this is true for any local operator A. Okay, so I'm going to define our index. So for this purpose, I introduce local twist operator. So theta, this function theta, the theta function is a function from R to S1, which I parameterize like this, which is 0 when x is less than x0, and which is 2 pi when x is larger than x1, and x1 and x0 are separated by roughly by the distance L. And I assume that theta changes very gradually. So the gradient is upper bounded by some small constant gamma. And I also assume that theta wraps around S1 once in the positive direction if x goes from x0 to x1. And then I follow the philosophy of Affleck and Lieb and define the local twist operator like this. This is basically the same as the twist operator that I mentioned in the introduction, but this rotation angle is now given by this general theta function. And again, I have this unit cell structure. So this is consistent with interpretation that 2j and 2j plus 1 form a unit cell. Okay, and because of this identity, you easily find that this is essentially a local operator. It's basically identity here and here. It's non-trivial only within this region. Okay, and also because of this transformation property, you see that gamma transforms U to U Dagger. This is very important. So if omega is invariant under gamma, then we see that the expectation value of U is real, okay? Because omega U is equal to omega U Dagger, okay? And this reality condition is very, very essential for us. That's very important. Now I am able to state my main theorem, okay? Let omega be a unique gapped ground state with energy gap delta E greater than 0. Again, for rigorous definition, please look at the paper or the longer lecture. Then for any theta function satisfying this, so actually you must take, we must take L large. So gamma must be very, very small when delta E is small, of course. And anyway, so I take any theta function satisfying this condition. Then I claim that this expectation value is non-zero. And moreover, the sign of this non-zero expectation value because this is real, I can talk about the sign. The sign of this expectation value is independent of the choice of this theta function satisfying this condition. With this theorem in hand, we can define a Z2 valued index for this unique gap ground state. How do you do this? Well, that's very simple. So I claim that this sign is independent of the choice of theta function satisfying this. So you pick any theta satisfying this. And if the expectation value is positive, you say that this index is 0. If it is negative, you say that the index is 1. Good. And of course, this is consistent with what we had for the Zach phase. So this expectation value corresponds to this one. And Zach phase is either 0 or 1 if this is positive or negative. So it's the same. And of course, of course, as usual, I call this trivial and this non-trivial. Good. And here's an important remark. It is believed that Z2 is the correct classification. Okay. So this is something I do not fully understand, but this is based on the Bourdism argument and things like that. And people believe that for the class of models that I consider here, Z2 gives a complete classification. So I'm very happy about this. And so this seems to be the complete classification. And of course, this is a simple remark. As for the SSH model, our index takes 0 and 1 for this trivial, two trivial and non-trivial extreme cases. Okay. Here's a very important corollary of the index. So I take a family of Hamiltonian HS where S runs between 0 and 1, which connects H0 and H1 continuously in the standard sense. Okay, what is the standard sense? Well, number one, for every S, HS has a gamma invariant unique gap ground state omega S with energy gap uniformly bounded from below. Okay. And also this must be a continuous path. So I assume that for any local operator, A, omega SA is continuous in S. Okay, so this is very standard. And if this is satisfied, you say that H0 and H1 are continuously connected. And corollary, very important corollary, which basically says that our index is topological, is that this index omega S is independent of S in this situation. I want to prove this, but I only have this space, but that is more than enough. Well, this is a proof. So we fix a theta function that satisfies this. So delta E0 is this. Then I will use this theorem for each S. Then, since this satisfies this, we see from theorem that omega S U theta is non-zero. And this is true for any S. Now, I have fixed theta. So this U theta is just a fixed local operator. And I assume that omega SA is a continuous function, of course. And then this is a continuous function of S, which is real and non-zero, the same continuity argument. And its sign, it can never change its sign. Okay, so that's a proof. That's a full proof. Okay, and also from this fact that you find that if H0 and H1 have different indices, then there must be a phase transition. They can never be connected continuously. So in between, there must be a phase transition. I remark that all this argument makes sense only in the infinite chain. Okay, because for example, this delta E0 can be very, very small as you want. Then you have to be in large chain. And in order to satisfy this, you have to take very small gamma, which requires very, very large L. Okay, so everything must be in the infinite chain. Actually, this is the only place that I must be in the infinite chain. Okay, and anyway, we have this corollary. So this is a slide that I have already shown you, but from this, we get this conclusion that H0 SSH and H1 SSH belong to different phases within this class. Okay, let me show you how to prove this theorem, but only in a finite chain. Again, if you are interested in the infinite chain, please look at my paper or the longer lecture. Okay, well, this is not difficult. So I consider a finite chain with periodic boundary condition, and this is the theorem that I want to prove. Okay, I first take a unique ground state, phi ground state with a gap delta E. This is a finite volume version of this. So omega is written like this. This is the ground state expectation value. And then I take a theta function satisfying this. And then I claim that by following Bloch and especially Lipschutz lattice, we get this energy estimate. What is this? Well, this is very standard. This is very standard and very elementary. But I claim, let me explain. So I first recall that both H and phi ground state are invariant under uniform U1 rotation. This is theta is a rotation angle. This is just a U1 rotation operator. But now we are applying to phi ground state, not this uniform rotation, but this U theta. U theta, the constant is just plus minus, is written in this way. So this is a U1 rotation with non-uniform angle, but I claim that I recall that this theta j changes very slowly from side to side. Okay, so this should change the expectation value H only by a small amount. Okay, now here we have a ground state, and here we have a variational state obtained by applying this gradual U1 rotation to phi ground state. And this is ket state. And here you have corresponding bra. You have the corresponding bra state. So this is the energy expectation value of this variational state. And this estimate shows that the variational energy is higher than the ground, larger than the ground state energy only by a very small amount, like this. And if you work out the constant, it looks like this. Theta prime is upper bounded by gamma. Okay, so this is a very standard Lipschutz lattice type estimate. Very easy to prove. Okay, so because of this assumption, we see that this energy difference is upper bounded by delta E. Now, I want to show that this omega u is not zero. So I assume that omega u is zero. What does this mean? Well, this means that the inner product of ground state and U phi ground state is zero. So this variational state is orthogonal to the ground state, but it has this variational energy less than delta E. Well, of course, this contradicts with the assumption that the ground state is unique and has energy gap delta E greater than zero. So this means that we were not able to assume this. We have proved that omega u is non-zero. Okay, the rest is easy. Again, the continuity argument. Okay, so omega u theta varies continuously when we modify theta function continuously. And again, this is real and varies continuously and non-zero. The sign can never change, QED. And actually, this is a proof for finite system, but the proof for infinite system is basically the same. It's very simple and still rigorous. Okay, so this is, I'm sorry, this is not the final slide. So before going into the final slide, let me state two theorems that I prove in my paper. The number one is something I call the duality theorem, which I find interesting. So let omega be the unique gap ground state. By using this twist operator, I define this index. But now you can use, for the same ground state, you can use different twist operator, U prime, which is defined like this. It's almost the same, but it's consistent with the interpretation that these guys, 2j minus 1 and 2j, form a unit cell. This is a different operator, and you get a different index from this. And now what I can prove is that if you sum these two indices for the same omega, of course, you get 1. This means that if this is 0, this is 1. If this is 1, this is 0. In other words, any unique gap ground state is topologically non-trivial, either with respect to this index or this index prime. Okay. I can also show the existence of edge mode. There are several versions of this edge mode theorem. This is one clean version with a rather strong assumption. So this is our Hamiltonian, but I further assume that it has translation invariance. There is an even constant R1, and both V and T are translation invariant. And then I take such an arbitrary Hamiltonian, and by H plus, I denote the corresponding Hamiltonian on the half infinite chain, obtained by simply restricting these sums to the half-infinite chain. Here's the theorem. Suppose that the ground state omega of H is unique in the global sense. I'm not going to explain. Please look at my paper. Gapped and satisfies index is 0. So it's topologically non-trivial. Then any gamma invariant ground state omega plus of this H plus is accompanied by a particle number conserving gapless excitation that live near the edge. More precisely, for any given epsilon, very small, positive epsilon very small, there exists a local unitary operator that lives near the edge, which generates a state which is orthogonal to the ground state, whose excitation energy is bounded from above by epsilon. Okay, for more details, you can look at my paper, but this is the statement. Okay, so like this is the SSH case, and you know that here's a zero energy gapless excitation at the edge, but I can prove that it's generic. Okay, now this is my final slide. I'm sorry. This is my summary. I have presented a rigorous but very elementary index theory that applies to a class of interacting one-dimensional insulator, topological insulator, I'm sorry, including the SSH model. And our Z2 index is defined from the sign of the expectation value of the twist operator. That makes the theory very elementary, still being rigorous. And the index is topological. And I have also shown that if you consider half-infinite chain, there is an edge state. Okay, so that's all what I wanted to say. Thank you very much for watching, and goodbye.